Okay, let's pick on example 12 here. On example 12, 400, a large one. Something gives you 400. Maybe the obvious one is 4 and 100. 4 is 2 and 2. 100 is 10 and 10. 2 and 5. 2 and 5. Prime factorization then of 400. We got a couple or several twos. How many twos? 4 of those. Pairs make perfect squares. For every pair, one number comes out. And we have nothing left over. So it's just like we did up on example 8 with the 3 root 25. We do not have a radical left over because 400 is perfect. If we continue down here on our perfect squares, 15 times 15 is 225. And if I continued on it, 20 times 20 is 400. 400 is a perfect square. May not have remembered it or noticed it, but that is the case. So 6 times 2 times 2 times 5 gives me what? Multiplied together, 120. So again, if you don't end up with anything underneath the radical, that means it was a perfect square, okay? Now let's continue on this, but these are not going to be perfect squares now. It's not a square root. It is a cubed root. So as you notice here, that little 3 there tells me it's a cubed root. Nothing changes. You're going to do the exact same thing. Instead of, though, looking for pairs, sets of 2 of the same number, you're going to look for triplets, sets of 3 of the same number. So we start off the same deal, 54. 54. Okay. 3 and 3. 2 and 3. So 54. 2, 3, 3, 3. There's my prime factorization of 54. And because it's a cubed root, I'm looking for triplets, sets of 3. So 3 times 3 times 3. I'm going to create myself a new sticky here. Sorry. Sticky. That's right in the way. Let me scroll this other one down. Or not. And then this one, come on. There we go. Okay, so 3 times 3 times 3, what we are getting into now is what we call perfect, it's a cubed root, perfect cubes. So 1 times 1 times 1 doesn't do much for us, but 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. 4 times 4 times 4 is 64. 5 times 5 is 125. Those are all perfect cubes. Now that's about as far as I can remember. So with these, just like you have perfect squares, we have perfect cubes, and it continues on forever. So in this instance, that 3 times 3 times 3, let's go back to the example, that is a perfect cube. For every set, one number comes out, for just like we did with square roots. So we had a 4 up front. We have a set of 3s here. So we bring it on out front because the cube root of 27 is 3. What number times itself 3 times? And then 2 stayed underneath because it cannot make a set of 3. And 12 and the cube root of 2. 64. 8 and 8. 2 and 4. And now the prime factorization of 64 is 3. Oops. Clean that back up. 2s and another 3 2s. Pairs. Ooh, I'm not looking at pairs, am I? I'm looking for sets of 3. I'm looking for triplets because it's a cubed root. Silly mistake to make there. For every set of 3, one number comes out. And we run into this idea again of there's nothing left underneath the cube root because 64, as we look back down there, is perfect cube. So 64 is a perfect cube, which is 4, and 8 times 4 is 32. Last one there, 250. Go for the obvious, 25 and 10. 25 is 5 and 5. 10 is 2 and 5. So the prime factorization of 250 is 2, 5, 5, and 5. I am looking for sets of 3. And -7 times 5 is -35, and the cube root of 2, because there's a lone 2 left over. Okay, that covers perfect squares and perfect cubes. We are going to primarily be working with perfect squares and square roots, but the cube roots will be popping up randomly, and as you get into Algebra 2, it will continue on. You'll go down further that rabbit hole, but we are just starting that process right now.